Now we're going to look at how we can compute a t-test checking for differences between dependent means. That is, how we can run a t-test where we are looking at paired data sets and wanting to measure a potential change. So for this, we have to be a little careful about how we enter things. There's a lot of choices that are somewhat arbitrary. We just have to be careful of being consistent, and I tend to follow a specific pattern. So here we're looking to see if shoes change vertical jump heights. So what we're going to do is go into the calculator, go into our list editor, and we're going to put these into list 1 and list 2, where traditionally you put the old one first and then the later one second, or that's before and after, or in this case old, new, however it's labeled, that's what you do. We're going to put these in here, and I'm going to make a mistake on one of them just to prove a point. But with these, the order, you have some leeway about making sure they go in the right order, and you could technically swap old with new in terms of which goes into which list, but it's the sort of thing where you really do have to be careful to make sure that things match up correctly, and whatever adjustments you make, you're going to have to counteract later. So even though in a sense it doesn't matter which goes first or where, you do want to be careful and consistent. So I always do old in list 1, new in list 2, just because having some measure of consistency here really helps. And it's easier to not think of these things as ambiguous, just to get into that fixed pattern. But anyway, once we have all of these in here, we're going to go into our third list, and we're going to make a list of differences, where what we do for that is we go into L3, then put in L1 minus L2. And we have to do this up in the L3 part, so it makes the formula for the entire list. Now, there are a couple different ways this can go wrong, so I'm going to clear out the list now and just show you. First would be if you don't go up into that list heading and instead just try and put it into one of the cells. So you put L1 minus L2 in here. In that case, you're trying to put a list of data into a cell. Those two things don't communicate in that way, so that's not going to work. The other thing that can go wrong is what happens when you enter a value incorrectly into the list, like I did right here in the second entry of L1 and the second entry of the old heights, whereas you can see that's a 2 and not a 22. So if I make the list of differences again, you'll notice that, well, the second one's a little bit big. And hopefully you'd see that even if you missed it earlier and go, oh, okay, I put this in wrong in list 1, then you'd fix it. And you might hope that that's all you need to do, but the problem is that once you make the list of differences, the calculator only treats this as a list of values. So if you want to fix that error, you'd have to go back in there and regenerate the list. Where I do L1 minus L2, traditionally I do old minus new, but again, you could flop it and go the other way. Just understand that whenever you do that, you might be looking for a different sort of tail than you would be if you went in the other direction. Anyway, here we've got our list. We've got all that, and what we're going to do with this list is run a t-test on those differences specifically. So we're going to go into stat again, go to our tests menu, pick the t-test, and here we have a data set. We're expecting no difference, so mu naught is 0. The list we're running on now is list 3. Technically speaking, if you're capable with your algebra and your arithmetic in your head, you could just make a list of differences directly from each of these, but I'm doing it the long way so that you don't have to worry about that. We don't mess with the frequency. And then for our tails, this is where the choice of L1 minus L2 or new first then old, old first then new becomes important, because here we are testing for an increase. Where if we are testing for an increase and we do old minus new, we should expect all of our values to be negative. So we'll want to run with a left tail. But again, that's a choice that we made that doesn't have to be done this way. We could do new minus old, or we could flop L2 and L1. However we want to do that, we could end up looking for the right tail instead, but with this setup, I'm looking for a left tail. Once we have that, we run this and we get our t-score here of about -2 1/3, where you'll notice it's a little bit easier than trying to do this stuff by hand. And also, I think it's more intuitive to think of this as a t-test on differences. But anyway, we get that t-value, and here we can see that that t-value is, for one, well below our critical value, where we can get that critical value in the same way, and I'll check that later. And also, it's smaller than our level of significance here, alpha equals 10%. Where, to be sure, since we're looking for that left tail, if we want to get the critical value for that comparison, that would again be something with inverse t, where in this case, because we have paired data, we only have one size for our sample, 8. So we would have 7 degrees of freedom, to go along with a cumulative area of 10% for a region with critical value about negative 1.415, which is bigger than our t-score. That is, our t-score is in the rejection region. So whatever justification we want for that, we are rejecting the null hypothesis in this case. So for our second example here, we are looking at a legislator who wants to see if there's any evidence of a change in performance rating, where here we've got a lot of data to track down, so you really have to be careful about entering all of this correctly, but it goes in much the same way as before. We go to Stat, Edit, we're going to put in our ratings, where I'm going to put the old ones first, so that'd be that 60, 54, 78, and so on. So I'm going to, speed through here just to save us a little bit of time, but I'll see you in a second. And then our last one in here is going to be that value 63, where I just check back up here and make sure that everything looks like it makes sense. And then once these are all in there, we're going to do the same thing in list 2 for the newer ratings. And once these are all in here, we're going to go back up and we're going to make list 3 our list of differences, where again, we could do list 2 minus list 1. I'm going to do list 1 minus list 2 just to be consistent. And we'll get that the differences here have that form. And again, it's a little nicer to do this in the calculator than longhand, but if you want to make that list yourself, you can make that list yourself. Anyway, we have this. We're going to run a t-test on that third list, where we are expecting no difference, or that's our assumption of no difference, and we are looking for any potential change, so we're going to keep the not equals option, which is the easier one to work with, and it's generally the more common one for this kind of test anyway. We click on that, and we're going to get a t-score of about 1.369, along with a p-value of about 19%, where that p-value of 19% is bigger than alpha, significantly bigger than alpha. And if we want to get that in terms of a critical value as well, it's nothing too special there. We're going to use the inverse t function again, where because we have that 1% level of significance, in terms of the upper value in the two tails, that's 0.995, and 15 degrees of freedom for 16 things. So we run that, and we can get that our critical value here, the breakoff for our critical region, is about at positive and negative 2.947, and our t-score is in between them. As a result, we have that there is not enough evidence to conclude the rating has changed, as we are, for either justification, failing to reject the null hypothesis.